Welcome students and teachers. We now continue our video on different parameters of a telescope and how that affects our viewing and observation. So, in this video we will focus on what are the important parameters of a telescope and how parameters like focal length, field of view affects our final observation. So, let us dive in. So, oftentimes in telescope near the end of the tube you will see some of the numbers mentioned and they quantify some of the important parameters of that telescope. We will look few of them one by one: resolving power, magnification, field of view, focal ratio, exit pupil. We should know what the focal length is. So, just to remind you that if parallel rays are coming to an optics, be it mirror or lens, the distance from that optics till where they converge or appear to converge, that distance is known as focal length. It is possible for diverging lens or diverging mirror to not have these lights focused, rather they appear to focus at that place. In that case, focal length will be defined as such. This focal length is a very important quantity for one of the useful parameter that we call magnification. So, we come to a useful quantity called magnification. It is calculated using a formula: focal length of primary optics divided by focal length of an eyepiece. So, if we consider this telescope, for example, it is called a finder scope. So, it has an the eyepiece, which in this case is the primary. So, whatever the focal length this primary lens is divided by focal length of this lens gives us the magnification of this finder scope. So, if I look at you, I see with a certain magnification. Let us say this number comes out to be 30, it is way less than 30 for this telescope, but if it comes out to be 30, what would happen? So, if there is a region on the moon that has angular size of 1 arc minute with 30x magnification, when this formula gives us 30x, that means that angular region will appear to us with an angular size of 30 arc minute, and so on and so forth with other magnification. Now, typically it is very difficult to change the primary focal length, but what astronomers do, they carry a lot of the eyepiece with them. So, they can, not for this finder scope, but they can remove the eyepiece and replace it with another the eyepiece to have a different magnification. This formula, primary divided by eyepiece, is true for both refractor and reflecting telescope. So, if you have an objective lens, when parallel rays come and they converge somewhere around here, although because of a mirror they converge at a different point, but this entire length will be our focal length of primary. Then this length where parallel rays converge it at from the eyepiece, this length is our focal length of eyepiece, and that governs the magnification of our reflecting telescope. However, a lot of telescopes, especially advanced telescope, have especially eyepieces use combination of different lenses. So, they use combination of lenses with different focal length. In that case, we use whatever the effective focal length of that entire eyepiece is. Okay. That will be used for that formula, and using combination of lenses have different advantages, which we will discuss in a different video. Okay. Similar thing we can have for the mirror and lens based telescope, which are reflecting telescope, and over here we will also have focal length of primary mirror divided by focal length of an eyepiece. Alright. So, one thing to note, that just by changing eyepiece and keep on increasing your magnification does not mean you will keep on seeing larger and larger images. It comes at a cost, because number of photons that the telescope is receiving and converging and focusing to the eyepiece will not change. So, when you have a larger magnification of, let us say, Jupiter for example, it magnifies with a different set of eyepieces on objective. Because this entire region will have the same number of photons, the relative brightness of this object, whatever we are viewing, reduces, and therefore, if we are using that telescope to look at a relatively dim nebula or a region, then using a higher magnification will be a disadvantage for us. One more thing higher magnification limits us is if you try to observe two nearby stars that are below the resolving power, no matter what magnification you use, that those stars will not appear to be resolved, because magnification does not change the resolving power. Resolving power is is dependent on only the aperture of telescope. So that is one important thing to keep in mind. It's a very common mistake students make. Right. One more things that get affected due to magnification is something called field of view. Now field of view is an angular region that telescope or binoculars are seeing. So if I look at some region in the sky, the angle that region subtends to the observer eye is called field of view. It is measured in degree or sometimes in arc minutes. And what happens if you are using a higher magnification, then you see this region apparently zoomed in. So what happens is that you see a smaller region but highly magnified. So your field of view, the region that you are observing, reduces. So let's talk about relation between magnification and field of view. So let's consider this eyepiece for example. Now if I try to look through this eyepiece from a distance, I am able to see certain region. Hi viewers. So this field of view, whatever I am able to see, that is my field of view. When this is a part of a telescope which has certain magnification, that field of view will reduce, and that is governed by this formula. We have something called apparent field of view, that is a field of view of this eyepiece that manufacturer measure and usually provide this information. Typically standard eyepieces come with field of view 50 to 60 divided by the magnification is what our true magnification is. So if you keep increasing the magnification, your field of view will decrease. So if you try to observe Andromeda and you try to photograph it, because from human eye you don't see the entire Andromeda like this, then if you use a higher field of view, you will be able to capture a much part of the Andromeda in a single image. But if you have a much higher magnification, you have to take multiple images across the Andromeda. That is one part to be taken care of. Moving on to another parameter called focal ratio. It is again defined by a formula, focal length of the primary optics divided by the diameter of the aperture. So this is the focal length of the primary optics divided by the diameter of the aperture where these incoming parallel rays are coming. That gives us a focal ratio. In this case, focal ratio is 4. The focal ratio is much larger, I will get a focal ratio. It is represented as f by 4, f by 8, or people who are interested in photography know this same quantity as f stop, but astronomers use focal ratio. What focal ratio determines is how bright the object would appear if to a camera or to an eye, depends on at what strength is the light is converging. Even with the same aperture for both telescope, in this case we will have a much brighter image compared to this image. So it could happen that you are observing Saturn with the same aperture, same diameter of telescope, but with different focal ratio. In higher focal ratio you will see dimmer image, in lower focal ratio you will, or people like to call it as faster telescope, you will see much brighter image. This is an important parameter to consider, especially if you wish to observe a dim nebula for example. So for that you will require a lower focal ratio. Also if you would like to photograph or do other observations, but for something like star clusters or globular clusters, higher focal ratio or slower telescope would be sufficient, or planets or moon or something like that. Right. Now for the final parameter of this video, there is something called exit pupil. So if parallel incoming rays to the primary optics hit and converge, finally they exit out at a much converged diameter, and this diameter is called as exit pupil. This definition holds for whether binoculars or different type of telescopes. If this exit pupil is much larger than the sensor or the eyes, then a lot of those light will go unnoticed, and such exit pupils are unnecessary for those observation. If they are much less, then the brightness that of our observed object is significantly reduced. If it is in the ideal range, you get a much brighter image, and it gives a nice observation or nice images for scientific observation. So if you, let's say, look at two different binoculars or telescope or eyepiece, this region that you see, this is how the light is finally converged enough for our eyes to see. So this has a much higher exit pupil. If this is within the range of our sensor or our pupil diameter, then we will see nice image without any light, where all the light is being used to form an image. In this case, typically the final observation will be less bright. Alright, that's all for this video. We will continue with more detailed analysis of what different design of telescopes are. Stay tuned. If you have any questions or any comments about any doubts regarding this video, or if there is any topic for which you require a detailed video for, please let us know in the comments. Thank you.